Thanks, Keith. Thanks, Sri. I did get the tutorial session on how to use this, so hopefully, let's see, we got a red dot? Yep, okay. As Sri indicated earlier, we use a suite of integrated models to answer this puzzle, this question of what impacts the water quality in the harbor, where the sources are coming from, how much pollution is getting into the harbor, what are the impacts of that pollution and those sources getting as far as water quality in the harbor, and then how do we analyze different controls when we project forward to the future. Whereas Sri focused earlier on the first part, the sources of pollution, how that gets into the harbor, specifically during wet weather, through CSOs. I'm going to discuss a little bit more today how we use tools to analyze the impact of those pollution sources on the water quality in the harbor. So New York City has been using mathematical models for water quality analysis for decades. What we thought we would focus on here are some of the improvements that have been implemented over the past couple of decades, so since 1990. The capabilities of water quality modeling have really vastly improved as the techniques have been improved and as computing power, computers, has really increased. So the table here shows 4 different models, and the hope here is that we can just demonstrate to you some of the expansion and the capability that has taken place since about 1990. The first one at the top is something we call SWIM. It's the System-Wide Eutrophication Model, and it is shown here. It is a very large-scale model. It goes out well into the Atlantic Ocean, down below Delaware and up near Massachusetts. It's a very complicated, complex model because it is designed to solve a very important and complicated system, and that is the dissolved oxygen system, probably one of the most important systems to water quality that there is. And to be able to analyze dissolved oxygen, you have to look at and analyze temperature, salinity, various forms of nutrients, various algal groups. There are many, it's a very complex system. So SWIM was designed to do just that, and also some other things such as bacteria and pathogens. We've used SWIM many times, still using it today. One of the most well-known applications, I think, was to develop a nitrogen loading limit for Long Island Sound. Okay, then we moved to 2002, and what we did in 2002 that I've shown here is a model called the Jamaica Eutrophication, the Jamaica Bay Eutrophication model. And really that was just a subset of the larger SWIM model to handle just Jamaica Bay. The improvement that we made into the model here was to be able to analyze that dissolved oxygen system better than we had before. Because in Jamaica Bay, there is something that happens that's important to that system, and that is the interaction between the sediments and the nutrients and dissolved oxygen in the water column. So we added that capability to the model because it was very important in Jamaica Bay. Project that was mentioned earlier today, biological nutrient reduction. That model was used for the BNR action plan for nitrogen for Jamaica Bay's 4 treatment plants that discharge to Jamaica Bay. The next model I want to discuss is it's very similar to the Jamaica Bay model, except instead of Jamaica Bay, we used it to focus on the East River. So it has the same sort of capability as the Jamaica Eutrophication model in that it adds that ability to look at the sediment interactions with the water column. And why did we do that in the East River? It's because of the tributaries to the East River. So we're talking tributaries like Flushing Bay, Flushing Creek, Westchester Creek, etc. In those areas, the interaction between the sediment and the water column is also very important, just like it was in Jamaica Bay. So to be able to handle those areas, we did another thing with the model, the system-wide model. We made it much higher resolution. So whereas before you might have one model grid spanning the area of, say, Flushing Creek, now you might have 10. Okay, so it's got a much higher resolution, and I was talking to some folks earlier before the talk. Over here is a board where we show some of these graphically. So we'd be happy to talk to you afterwards if you want to see some examples of that. And I have a couple of examples here. Next, we have 2010, where we made a further improvement to the Jamaican Eutrophication model. And this is kind of an interesting application. DEP was looking at the sustainability and possibility of creating artificial reefs in Jamaica Bay so that we could improve water quality in a more natural way. And that is, filter feeders filter the water. They take particulates out of the water. Would it be possible in Jamaica Bay to seed artificial reefs and have them self-sustain by, when they reproduce, they release larvae into the water column. If those larvae can hang around long enough to attach to the reef, then that reef system could be sustainable. So DEP looked at that question with this enhanced model of the Jamaica Bay area. So not only did we add systems to look at larvae, because larvae behave in funny ways, but we also increased the resolution here. And as an example, I show this is the way it was, and then this is the way it is. And from back in the back, you probably can't tell the difference. But afterwards, come on up and we'll show you. Here's another example. This is one we're working on right now, and it is for the Little Neck Bay Alley Creek area. On the left, you see the model segmentation that we used to have as of approximately 2008. And on the right, you see what we've done more recently, just within the past month or so. So why do we do this? We do this because now we can more accurately put the loadings that come in the right place. We can more accurately show the concentrations in the water. We can calculate those concentrations better in space and time, both along the shoreline and across the water body. So hopefully this makes sense. This is why we do these things. Okay, so we have these great models. How do we know they're any good? Well, that's a very good question. So what we do is we compare the models to the data. Okay, we go out and measure data, and we compare the model calculation to what we actually measure. And that process is called calibration. So what do we calibrate with? What data is out there? Well, since about 1909, the city has been collecting water quality data throughout the harbor. Now I think we have on the order of 75 water quality stations that are shown there on the left-hand graphic throughout the harbor. These water quality stations are sampled year-round. It's sampled a little bit more often in the summertime during warm weather, but year-round we have these samples. So it creates a very good picture and database of the actual water quality across the harbor. In addition to that, DEP is sometimes interested in a particular location, and when that's the case, they will do what we call a special survey or a special study in that area. And on the right, I show a demonstration here for Little Neck Bay and Alley Creek, because they're doing this right now. In addition to the three regular harbor survey stations, there are now 12 special locations where we're collecting additional water quality data. That will allow us to have a much more robust calibration of the water quality model for this water body. And here's what a calibration can look like. This slide demonstrates how we use the data and the model together. We do model comparisons to see how well the model predicts actual conditions that are out there. On the left, we see some panels, and what am I showing here? This is basically a snapshot in time, of the water quality for 3 different parameters here. The water quality in the East River. So we start at one end of the East River and we go to the other end of the East River. And this shows how the concentrations vary in the top and the bottom. The data are shown here with arrows, and the model is shown here with lines, and we have top and bottom. So if we can capture those gradients from one end of the river to the other end of the river, and we can capture where we have what we call stratification, a difference between the top and the bottom, then we consider that a good calibration. Now that's one way to look at the data. Another way is you pick one spot, right here for example. Here is a spot, and that's the East River at Little Neck Bay. And at that one spot now, we look at how it varies over time. So what's shown on the right here are the water quality sampling data points over the course of an entire year. Here's one that shows a good variation over the year. Data, and again, model. So it's the same thing. Does the model capture what's happening with the data? Now, Sri discussed a little bit earlier how they do that with the hydraulic models that he discussed. With water quality, it's very complex, it's difficult to do, and as far as I'm aware, there are no metrics that are out there that are accepted metrics that says it's good or it's bad. So what does DEP do? Well, they convene water quality model evaluation groups. And the history, the city has a long history of doing that on many of the projects over the past couple of decades. So to make a long story short, we have experts from third parties that come here from academia and industry and other areas of the country, and they take a look at what we've done, they give us suggestions, they evaluate what we're doing, and they either say it's no good or it's good, and I'm happy to say that we have very good experience. We even won an ASCE award in 1999 for the modeling that we do. So we feel pretty confident with our ability to at least say what is going on now. And if we can say that our models have the ability to predict what's going on now under existing conditions, then we believe that if we invoke changes to the system, if we put in a tank, if we have green infrastructure implemented in the city, then we can project to that future condition and predict with fairly high confidence what will happen. So that's the name of the game. That's what we do here. And I think, Sri, you're going to take the next step.
Thanks, Tom. Once the models are constructed, we use them to assess the baseline water quality conditions. What is considered as baseline, through the consent order process is the projects that we have already committed as part of, what we call as the cost-effective gray strategies from our watershed water body facility planning studies, and also the 10% impervious cover reduction or management of 1 inch of stormwater in 10% of the drainage area, impervious drainage area within the combined sewer system. So these become, our baseline assumptions, and we want to review some of those assumptions in detail here, because this forms the foundation for our long-term control planning process for each and every water body. So we start with what the committed cost-effective gray projects are and the green infrastructure element in that watershed, and then assess the water quality conditions, and based on the designated uses, whether it's a fishable swimming pool or other, we look at what the gap in terms of achieving that water quality goal is. So we start with the rainfall conditions. The city has used 1988 John F. Kennedy Airport data as the average conditions so far, consistent with a lot of harbor-wide studies. But there's a recognition that there's an increased rainfall conditions in the recent years and so on. So we undertook statistical analysis in the recent years, in the last 2-3 years. And we looked at the data for over 50 years at all the 4 metropolitan gauges. And we evaluated them in terms of, can we include the more recent wet weather periods for our planning level analysis. And then also for considering the climate variability as one of the sensitivity analysis in this baseline projections. So this shows, in general, the 1988 rainfall that shows up here. And the y-axis is the annual rainfall, and this is the timeline. And the average that has been chosen from a recent analysis is 2008 John F. Kennedy Airport data, with a total annual volume of about 46 inches in comparison to 40.6 inches that were used in previous studies. So this itself is giving almost 15% increase in the annual rainfall that we will be using in the baseline conditions here. The next step is, what are we going to do with these data sets? The calendar year 2008 data is going to be used for screening and selection of alternatives when we do this long-term control planning. And then for assessing the compliance to the dissolved oxygen water quality standards, because the eutrophication modeling that Tom mentioned, they take a lot of significant computational effort as compared to the pathogens. We use that 1 year period to assess the attainment of DO standards, dissolved oxygen standards. On the pathogen side, we look at 10-year variability from 2002 to 2011, and we look at the compliance on an entire 10-year period. Another input necessary for this is, the sanitary flows. For the current evaluations, we use, what is measured at the treatment plant. But for future conditions, we worked, or the Transportation Council, Metropolitan Transportation Council, and the city planning worked on wastewater projections for the different drainage areas. And we are using the projection for 2040 as the basis for the baseline conditions. So this slide and the next slide have some assumptions that we are continuing to discuss with DEC. And one of the assumptions is the treatment plant capacity. You're using the 2 times design dry weather flow as the plant capacities. And the basis for that is that this is an example of plant inflows that we see at Red Hook treatment plant. The dots are the measured values, and the solid line is the modeled value. So generally, for the rain events, we are hitting 2 times design dry weather flow, either at that level or in excess at this treatment plant. So on an annual basis, we show a comparison between monitored and modeled data. Again, you see a decent correlation, and then going in excess of the 2 times design dry weather flow value. That's the basis for our assumption here. And the next assumption is also one we are discussing with DEC. This is the sediment conditions, one of the questions raised here earlier. We had interceptor sewer cleaning process after undergoing an extensive sonar inspection of the entire interceptor sewer system, these dots that you see here. And after the cleaning process, we are assuming the post-clean sedimentation levels as the basis for interceptor sediment assumption. And then on the combined sewer system, there's no sedimentation that we are using in this baseline process. Green infrastructure is a major element of this baseline. And what we see here is the targeted acreage management for 1 inch of stormwater for the different water bodies here. And we are undertaking 3 different strategies. The right-of-way bioswale, that's looking at the storage solution, storage infiltration solution. Then on-site public and on-site private that are looking at detention to slow down the water, not necessarily storing and eliminating them from getting to the sewers. So this is the current status. The future status will involve the remainder of the 10% impervious cover that we need to manage. It also includes the capital gray infrastructure projects that have already been committed. This is a series of those, the ones that have been already built, like the Paragat Basin here, Alley Creek Retention Facility. Then there are going through active construction, like the Gowanus Pump Station, and then upcoming construction projects also. So just a quick summary of how we model the green infrastructure. I'm going to be making it really quick with the timeline that we have. One announcement that I need to make is this entire presentation and also the video recording. They are going to be available in our website. We may be kicked out a little after 8 o'clock. In that case, we may have to continue either in the hallway or follow up later. So this is what your detention practice is at a development site, for example. So you have this stormwater coming into the detention practice. There is an infiltration that may happen, and there is a constricted outlet that delays the flow from getting into the sewers. And then for large storms, you have a relief pipe that also can get the water down to the sewers. So this is at a single practice level, but at a bigger scale, for the subcatchment scale or sub-basin scale, we lump them for the different detentions that will be happening based on the number of construction projects that will be ongoing in that area, and then lump them and then represent the reduced, the 0.25 CFS per impervious acre, and such targets are built into this sizing of this smaller orifice, and then the overflow pipe. And same thing with retention practice, the bioswale schematic that has the infiltration and then the storage at a single site scale, and that gets lumped in with the corresponding storage and infiltration characteristics before the flow can go to the sewer system. So we implemented all these into the citywide baseline. We ran all the 13 different models, actually 12 of them with combined sewer systems. And what you see here is an annual overflow volume from each of these wastewater treatment plant service area. So these include the baseline inputs like the 2008 rainfall, 2040 dry weather flow, etc., including the current phase of the GI implementation that I showed in slide 38, post-clean sediment conditions in interceptors. So this 20 billion gallons of overflows is what is our baseline CSO flow conditions on a citywide basis. And then summarizing them in a different way in terms of the water body, for the Alley Creek, Bronx River, etc. Again, that total remains the same, but it gets distributed among the different waterways. Next steps. We are continuing to perform the pilot monitoring efforts that some of our academic partners are helping with, some of our industrial partners are helping with, to understand the performance of the green infrastructure projects in managing 1 inch of stormwater. How successfully are they able to do? This is what our research project is on, or the pilot projects. So that's, we are doing over 25 of these pilot projects, and we are also doing this neighborhood scale that I just mentioned about in 3 areas involving number of installations. It's not one right-of-way bioswale, but a number of them. Some also have the porous pavers within that drainage area and so on. So we are able to see the performance of this collective set of green practices to achieve the 1 inch of stormwater management. So based on the lessons that are learned from here, we will be varying the performance. Instead of the current modeling assumption that we are able to retain or detain 1 inch of stormwater, we'll be using these to, as a reality check, to modify those assumptions, either based on the number of right-of-way bioswales going into one area versus, multiple boroughs, accounting for the infiltration characteristics, Jamaica versus Bronx, that type of spatial interpolation. We also will be doing targeted flow monitoring program, or either as part of the post-construction monitoring or to gather more information about the system. Tom mentioned about this targeted monitoring in Alley Creek, Little Neck Bay, but that is more on the stream or the ambient water quality monitoring. There's a parallel effort that went in to look at what is coming from stormwater outfalls and quantifying the characteristics of that, how much of fecal coliforms, enterococcus are coming from these stormwater sources versus the combined sewer area. So we will continue to use this information to update the InfoWorks models as we go into the long-term control planning process. Alley Creek is the first example where you saw the additional monitoring needs. Similarly, as we undertake, we're depending on the data gaps that we identify, we will perform additional monitoring and use them to improve the modeling setup at a local scale. Post-construction monitoring, this is an effort in Alley Creek. So this basically provides measurements not only at the tank in terms of how much is it capturing, but also we are able to relate in the water quality or the ambient conditions to see the improvement in water quality conditions before and after the construction of the projects. So we will be doing for a certain period, 3 years, 5 years, depending on the permit duration. But then these information also are helpful in updating and calibrating the model further, so we can continue to use the models as a way of doing the performance assessment, once the PCM monitoring is done. So with this, I'm going to rely on Sean to, Shane to get us out. But until then, we can answer any questions that you may have.
Pretty basic question. In terms of your analysis of the capture of stormwater at GI sites, looking to monitor the ability to capture the first 1 inch, to what extent will you be also measuring the additional capacity of capturing stormwater at those sites? So if you're looking for 1 inch, but the site is capturing 1.5 or 2 or 2.5 inches, will you be monitoring that or being able to assess that?
I don't know. Angela, you want to work? Because we have talked about a few strategies. If you want to.
Well, I mean, two major responses that I would give is one, we have done some monitoring on an individual basis, and we are planning to enhance that type of monitoring using various instrumentation techniques through a research and development program. So I don't want to say too much about that. It would be a future contract, but we do plan on enhancing that. We see the need for it, and we do plan on doing more.
And but part of it is also related to the catchment area. Sometimes we assume that this is what is getting to a specific right-of-way bioswale that we are monitoring, but maybe it is capturing the real drainage area because of the slope and so on. It may be a much larger area, so we see the performance, we are able to see it. Even then, the performance monitoring report that we have in our website, you can refer to that. Many of our practices capture well in excess of 1 inch.
Go ahead. A related question about, you said in the previous 30 years, up until 2002, we had 40.6 inches on average per year. But from 2002 to 2011, we had 46.3. But when did you come up with the standards of capturing an inch or 1.2 inches? I'm wondering about whether we've adjusted the standards based on that, whether we're designing to the right level. And I shouldn't be asking that question for using standards, but are we designing to the right level?
Yeah, good question. This is something I have seen in a number of states. Commonwealth of Virginia and New York State. New Jersey. Generally, 1 inch is considered as if you have 100 events or 110 events in a year, 90% of the storms are less than that. So that is considered as the water quality. Storm volume, or if you're sizing for the water quality. So I don't think that will necessarily change. This is more like, okay, have we seen increased frequency or number of events? But I'm not sure if we have stats on the last 10 years of how many events and whether that is still comparable to 1988. We had about 100 events, for 1988. I want to say that's going to be pretty much in the similar range, yeah.
And there's obviously a number of ways to go on this, but one would be to simply use your model and imagine that you put in, say, I don't know, something like a number of those, one of those every 1,000 feet in your model. That would be 30,000 in the whole city too many. But basically, you could look at that as a means for reversing output from your system simply by assuming that you put in the system with a certain capture size. We actually, with the DEC built, we have one road with 6 retrofit million trees and 2 like that. And so it's a way to get that kind of fine grained, even without having to build them all out now to look into the future. Right. So you potentially use your model prescriptively using brings to that, yes?
Yeah, we make, as Angela mentioned, we'll be refining that also. For example, you have seen the standard bioswale design from Mark D's group. He's now going with a supercharged design that is supposed to be a lot more, capturing a lot more water. And he's going to be also increasing the density to be able to capture them. So he's really targeting close to, a large fraction of the right-of-way to be controlled by this bioswale. So I think that will certainly improve, the way, because, what you see here, I mentioned directly connected impervious area, right? A large fraction of that is going to be the right-of-way area that's sitting right next to the catch basins and so on. Rain gets into that right-of-way as compared to, roofs and others that have a different mechanism.
Given climate resiliency and adaptation is a very popular topic now, I'm wondering how the long-term control plan will respond to the evolving climate as well as the models.
Actually, there's one slide that we have. I wanted to actually have that as part of our discussion, but this is more like a sensitivity analysis that we are planning to undertake as part of the long-term control plan, but it's not going to be necessarily used for evaluation of alternatives, but evaluation of alternatives will be done using the 2008 data that we have chosen as the typical year. But we are planning to use more severe 2005 data that, if you look at it on an annual basis, on an annual basis, that's quite comparable. But the thing is, the annual rainfall, what we chose as the 2008, is about 46 inches, and then 2005 gives that central scenario of close to 10% increase in the volume. And similarly, you will see the intensity to be a little higher also. So our plan is to use 2005 as a sensitivity analysis to understand how the sizing of our facility based on the 2008 typical year would function. That's the way we are planning to address. And this includes, as you could see on the top, not only the rainfall, but also a 0.8 feet adjustment to the sea level rise to reflect the sea level rise.
Okay, so this is not a model question. This is about just the general long-term control plan process.
Okay.
You pointed out the 1994 guidelines that were developed by, I guess, a federal act. The second goal, or I guess, process in developing a long-term control plan is to be involved in a public participation. I was wondering what that means. What format will that take, and what are the goals of involving the public in that process?
Hi. So we have a continuous outreach program. I mean, we have, this is outreach that we're doing right now. So one of the things, as with Alley Creek, we had a kickoff meeting at Alley Creek at Alley Pond. We will be following up that with, we've actually supplemented that with some briefings to elected officials, community boards. Tell me if I'm not asking a question.
Well, is the public involvement a dialogue, as in like a two-way conversation, or is it just telling us what's happening?
No, it's a little bit of both. I mean, obviously we have a lot of information to share, but one of the things that we want from you, and when we do local, for the Alley Creek and some of the individual, for each individual one, we want to hear what individual uses, people have, residents, users have of the water body and watershed area, which will help inform us in terms of the alternatives that get produced and in terms of what, and so we'll feed into some of the modeling of what we need to be doing. So yes, the answer is yes, it is a two-way dialogue in terms of we want to hear from you. So that's why we have the website, we have the
email, we have, we'll certainly be providing this. We want to inform you, and then we want you to come back at a later date, certainly when we do the individual LTCPs, tell us, what, the track that we should be taking. At this point, actually, we need to wrap it up only because we have to vacate the space right now. But that doesn't mean that we won't be continuing the dialogue. Like Shri said, we will have the presentation online. We will have it both as video and as a PowerPoint. And so we'll look forward to hearing from you